We propose a spatial augmented reality technique to fool deep image classifiers with a projector. For image classification, we input an image X to a deep image classifier F. The output has the highest confidence in the label Panda. Adversarial attack aims to add slight perturbations, delta, to the original image X. Then the perturbed image X' can cause the image classifier to misclassify the input image as a gibbon. This is digital adversarial attack, which requires direct access to the classifier's input image X. However, usually we don't have direct access to the digital images. Instead, we can only modify the physical environment of the scene by injecting adversarial objects or changing the light condition. For example, we can place a printed adversarial patch in real scenes, such that the camera-captured scene is classified as a toaster instead of a banana. Or to evade unauthorized face recognition systems by wearing an adversarial eyeglass frame. Similarly, users can wear a special shirt to evade object detectors. Lee and co-authors altered camera-captured scenes by applying a translucent adversarial sticker to the camera lens. Compared with physical ones, light-based adversarial attacks modify only the environment light condition instead of the physical entities, thus they can be more flexible and transient by changing the projected patterns. For example, Nichols and Jasper achieve untargeted attacks with a low-resolution projector camera system, where only one projector pixel is projected to the car. Shen and co-authors control camera shutter speed to capture human imperceptible adversarial patterns. Nguyen and co-authors project strong adversarial patterns to fool face recognition systems, while Zhou and co-authors use infrared LEDs instead, for better stealthiness. Unlike digital attacks where perturbations can be easily made stealthy, subtle physical and light perturbations are hard to capture using digital cameras and can be easily polluted by sensor noise, lens distortions, and camera internal image processing pipeline. Thus, to improve robustness against these factors, most existing physical and light-based adversarial examples are designed with strong artificial patterns, while stealthy attacks remains an open problem. In this paper, for the first time, we formulate the stealthy projector-based adversarial attack as an end-to-end differentiable process, and propose a method named SPAA, which has higher attack success rates and meanwhile being stealthier. As shown in the figure, our scene consists of a projector, a camera, and a soccer ball. Denote the camera-captured scene image as IX. If we input it to a deep image classifier F, the output shows that the label soccer ball has the highest confidence, which is correct. Projector-based adversarial attack aims to project a stealthy pattern X' to the scene, such that the camera-captured scene IX' is misclassified as a table lamp. Note that the adversarial projection is exaggerated for better visualizations. To solve for the unknown adversarial projection pattern X', we can iteratively optimize it by minimizing the loss between the classifier output label and the target label, until the classifier output is table lamp. But the real project and capture is non-differentiable, thus we cannot simply use gradient-based optimization methods. One solution is to include the real project and capture process in a gradient-free optimization pipeline, for example differential evolution. Due to the high computational complexity, this approach is limited to low image resolutions, and only perturbs one projector pixel. Even so, it still suffers from low attack success rates, and the projected magenta square on the soccer ball is clearly not stealthy. Another solution is to first perform digital adversarial attacks on the original scene, then use a projector compensation technique to solve for the corresponding projector input image. However, this two-step method is problematic, because digital attacks may generate physically implausible adversarial examples. Our SPAA approximates the real project and capture process with a neural network PCNet, thus the whole system becomes end-to-end differentiable, and both gradient-based optimizations and physical constraints can be applied to projector-based attacks. Similar to CompoNet++, we first project and capture a series of colorful texture sampling images to the scene, then we train PCNet to simulate the real project and capture process. The inputs of PCNet are a projector input image X, a camera-captured scene image IS, and a projector direct light mask IM. The output IX hat is an inferred camera-captured scene. PCNet has two modules, Warping Net and Shading Net, where Warping Net warps the projector input image to the camera canonical front view, and Shading Net transforms the rough shadings and the scene image to a photorealistic camera-captured projection image. We train PCNet by minimizing the similarity between the model-inferred camera-captured projection IX hat and the ground truth real camera-captured projection IX. Once PCNet is trained, we replace the real project and capture process with it, and use gradient descent to perform projector-based adversarial attacks. Inspired by PCNet, we optimize the adversarial projection by alternating between the minimization of adversarial loss and stealthiness loss. Finally, we project and capture the optimized adversarial projection X' to the scene for testing. In quantitative comparisons, our SPAA clearly outperforms the baselines by higher attack success rates and stealthiness. We show comparisons on targeted projector-based adversarial attacks. The goal is to use adversarial projections to cause the classifier to misclassify the bucket as mushroom. The 3 rows present results of our SPAA and the 2 baselines, respectively. The first column shows the camera-captured scene. The second column shows projector input adversarial patterns. The fourth column presents the scene under projector-based adversarial attacks, namely, the second column projected onto the first column. As shown in the fourth column, both baselines fail in this targeted attack, because their real camera-captured projections are classified as paintbrush rather than mushroom, while our SPAA successfully fooled the classifier. We also show untargeted projector-based adversarial attack. The goal is to use adversarial projections to cause the classifier to misclassify the camera-captured scene as any label other than lotion. This task is easier than targeted attacks. As shown in the fourth column, all 3 methods successfully fooled the classifier, but our SPAA looks stealthier. In summary, for the first time, we formulate the stealthy projector-based adversarial attack as an end-to-end differentiable process, and propose a method named SPAA, which has higher attack success rates and meanwhile being stealthier. Thank you.